All right, so let's open the floor for questions and discussion on the material that we have discussed so far. Just to summarize, we basically been talking about data flow analysis in a lot of detail, and that is because data flow analysis is a very fundamental, important technique in compiler analysis. It's basically, you can think of it as the mathematics of program analysis, right? Discrete program analysis, and so we need to really understand the mathematics. So we did that using first examples. Even there, when we are talking about examples, we looked at different ways of representing DFAs, and now we are actually doing the theory behind it, so that we can kind of have a common framework in which we can reason about everything. So yeah, let's open the floor for questions. Yeah, Arpit.
Yeah,
Yeah,
so
so
notice that.
notice that
Sorry,
again,
yeah. So like I noticed that for forward DFAs, we for like other than the boundary condition, we are only initializing the out of each basic block to the top value and not the in. And for backward DFA, we are only initializing the in to the top value and not the out. So is that any reason for doing that? Because initially we were initializing every other value other than the boundary condition to the top.
Okay, great. So the question is that, do I need, so for a forward data flow analysis, is it enough to just initialize out and similarly for backward data flow analysis, is it enough to just initialize the ins, or should I initialize all of them? And does it matter? So the answer is actually it shouldn't really matter, right? Because once you have outs, the first iteration is just going to meet over the outs and give you the in the forward data flow analysis. And similarly, so I'm just going to talk about the forward data flow analysis, and things just kind of have a duality in the backward data flow analysis. But if you initialize the outs, then ins are just obtained by just meeting over all the outs of the predecessor, and that if you initialize all the outs to top, then ins are all automatically going to be top, right? I mean, that's basically the idea, because there's no transfer function here between the out and the in. So we just didn't specify it, but you can, I mean, it's not going to give you any different answer whether you initialize in or not for a forward data flow analysis.
Yeah.
But yes, I mean, conceptually speaking, it's good to think about it that you have just initialized everything to top except the boundary condition, including out and in. Just the way I'm describing the algorithm, if you just initialize the out, the in is going to automatically become. If you initialize out top, then in is automatically going to become top.
Right. I had another doubt that given the semilattice definition that we had, like does it guarantee the existence of a unique top value and a unique bottom value? And if so, like how?
Okay, that's a great question. So does the semi-lattice definition guarantee the presence of a unique top value and a unique bottom value? The answer is no. I mean, I could have, I mean, what is a semi-lattice? Is a set of values and a meet operator, or a set of values and a partial order operator. And I could have I could have multiple elements which are not less than equal to any other element for in the lattice, semi-lattice, because it's a partial order. Though they don't need not have relative ordering between them. But but if such is the case, then I mean, from a data flow analysis point of view, right? So semi-lattice is one thing, but from a data flow analysis point of view, I would like to have unique values for initialization, for example. And so, for example, if you recall the constant propagation analysis, right? We just added a value called top, which was basically it hasn't been reached so far, right? I mean, that was just to make sure that we have a unique value which is kind of over and above every other value in the set of values. So you just typically design your DFA, and when you're designing your DFA, you're basically choosing the values set V and then you're choosing the meet operator, right? So when you design this for a DFA, then you would typically want to have a unique top and a unique bottom, right? And in fact, if I think about it, if it's if it's maybe you don't need a unique bottom, but at least you need a unique top.
Right. Yeah. Got it. Thanks.
Thanks for the question. All right, Anirudh.
Okay, so I have two questions. I'll start the first question. So basically, I wanted to, I've had the worklist algorithm. It basically does not check each program point at every iteration, right? So, like, is there an argument that proves, is there some sort of proof that proves that the worklist algorithm is equivalent to the algorithm that we had learned before, the algorithm that checks all the program points at every iteration? Because I was thinking, like, is there a possibility that the worklist algorithm, the worklist might get empty for some program, for some program, the worklist might get empty before the algorithm has checked all the program points. So, like, if that happens, is that okay? Or like, is there an argument that can justify that both those two algorithms will generate the same solution for every program?
Okay, that's a great question. All right. So yes, I mean, I think you've already pointed out to an example where the two algorithms can produce different answers, right? The example is the following, that let's say, my graph is disconnected, let's say, or something like that. And then I run the work list algorithm, and so it's not never going to reach the other half. So let's say I start from the top. I'm assuming a forward data flow analysis. Start from the top, and there are two halves to the program, and they're disconnected. Then I'm not, with the work list algorithm, I'll never get to the second half because it will never change, right? Because there's no connection to it.
Yeah.
But on the other hand, if I use the first algorithm, which is I use all the points at all the iteration, then I'm also kind of potentially changing the second half, because some of our rules could be, some of our transfer function rules could be that, for example, for constant propagation, if I have a statement called x equals c, then transferring across x equals c, even the top value gives you something which is not. Now, this basically, the answer to this question actually depends on the way you have defined your transfer functions. If you assume that if, for a forward data flow analysis, if the in is top, then the out will always be top, then I claim that the two algorithms would be equivalent, right? Okay, I mean, firstly, you need to understand the claim, then I'm going to give you the argument for the claim, right? But if basically top cannot go to anything else, right? It can only go to top across a statement. Then that basically means that stuff that is top that hasn't been made non-top can just be left alone. I mean, we don't really need to bother about it, right? And so that also gives you the argument of equivalence between the two algorithms, because worklist algorithm is basically saying that, okay, let's only look, I mean, as Namrata said, right, just look at those program points which can potentially change. And stuff that can potentially change is only the stuff that is, in the first iteration, it's only the stuff that's not top. Then after the second iteration, it's only the stuff that has changed in the previous iteration, and so on, right? And so that is, you can basically give an inductive argument which says that, okay, let's say, in the first iteration, what are the things that can change? And then say, okay, it's only the first thing. And then, if and I minus one, so these are the things that had changed, then what are the things that can change in the next iteration? And so you can basically use some kind of inductive argument to show that the two algorithms are equivalent, and you probably want to do induction on the number of iterations the two algorithms execute, right? Something like that. Yeah.
So I have a follow-up question to what you explained. So I probably did not understand your example where you talked about two disconnected graphs, and there the first algorithm will make changes in the other part of the graph, but the work list won't. So do you mind like explaining it a little more, or
Sure. So I think, we have, maybe constant propagation was not the right example to say that, but let's say liveness, for example, right? So in the liveness analysis, we have two values. Let's say I'm just interested in the liveness of a single variable, right? So then we have just two values, true or false, whether it's live or whether it's not, right?
right?
And false is, so true is less than equal to false, right? And true is the conservative answer. Everything is live is the conservative answer. So in this case, I mean, if I do a backward data flow analysis for liveness, and let's say I have two disconnected graphs, I start from the exit of the program, then I would basically say that everything in the first half of the program is not live at all, right? Because I just initialize it to top, and then it's just not live forever, right? In the work list algorithm. Does that make sense? See, the two graphs are disconnected, right? So, and the boundary condition was in the second half, the second part of the graph.
Okay.
So it's only the second part of the graph that can change because there is no edge between the second part and the first part. And so the first part would just remain static all the time, right? And it'll never change in the work list algorithm.
I see. So if I understand it correctly, you're defining the boundary condition only for the second part of the graph and not for the first part of the graph, or?
Yes, the boundary condition for any DFA is, for a forward DFA, it's always on the entry or something.
Yeah.
Typically, and then for the backward DFA, it's on the exit. So if you have two disconnected graphs, subgraphs, then of course exit is going to be part of only one of those, right? I mean, these are kind of disconnected subgraphs. So whichever, for a liveness analysis, I'm only going to look at the subgraph that has the exit, and that's it, right? Does that make sense, or no?
Maybe I'll follow it up later. I think I'm still a little confused at this point of time. Yeah.
Okay, all right. We can talk about this.
Yeah.
Sure.
So basically, if I may, so basically, this is an example where the worklist algorithm and the previous algorithm, fixed point iteration algorithm, will differ in results.
Yeah, I mean, see, you can define a DFA in the most general sense, where you could potentially create situations where they kind of give different answers, but those answers are not going to be. I mean, it's just that you defined it in a certain way. It wasn't really very meaningful, right? Because you could have defined it in another way, in which case they would have been equivalent, and the answers would have been still equally good, right? Or even better, in fact, right? So yeah, I mean, I was just saying that how are we going to go about proving something like this? And what properties you need. I mean, just kind of giving you a sense of that, basically.
Yes, sir. Thank you. So I had, like I said, I had another question. So basically, like we had defined the meet operator with respect to the semi-lattice diagram as the first common descendant of the two nodes, right? So what if there are multiple first common descendants? Is it possible at all for the graph? Like, for example, like X, Y have first common descendant, they have a first common descendant as Z1, and there is another first common descendant as Z2. Is it possible in a control in a semi-lattice diagram, or if not, like if there is any property that forbids that?
All right. So we need an argument which says that the first common descendant is unique, right? Does anybody want to take that challenge? Yeah, I need to think myself as well. Give me a second. Yeah. That's a good question. Okay, yeah, that's a good question. I'll need to think a little bit more to answer that, and let me get back to you on that. Yeah, thanks.
Right.
So I just had a doubt in previous question, which you answered. So if two code, like if the graph is disconnected, doesn't that mean that it is a dead code and we don't need to go there?
Exactly. So that's the reason, right? I mean, I'm just saying that if the graphs are disconnected, it probably means that some part of the graph is basically dead code, and we really don't care about it, and we can leave those values at top. It's just a matter of how you mathematically formulated your DFA. And if you and you can formulate it in such a way such that the two algorithms will give you the same answer. So indeed, I mean, that's why the workless algorithm is useful, because if it differs from the original algorithm, which was going to look at every point at every iteration, then it's going to it's going to be for graphs where we really didn't care about those answers. That's what it meant. Does that? I don't know if this is confusing, or and I can be more detailed about this. So does it?
No, sir, that's fine.
That's,
Didn't we like add two special entry and exit nodes that there is only one entry and only one exit? So wouldn't that just connect the disconnected graphs? Like if there was a single exit node, that would basically just connect both the disconnected graphs, right?
yeah, that's true. Yeah. So if we just basically add, yeah, but I mean, it's so yeah. I was just giving a hypothetical example where there's some dead code in the thing, and you've been able to figure out that it's dead code. You have removed the edges, right? Now you don't want that entry to jump to that part of the code. I mean, in the real program, it's not going to jump there. It's just dead code, right? So yeah, I mean, it was just an example. When you talk about formal properties, I mean, you talk about proofs, right? Then you want to have some. I mean, you just want. I mean, you want to basically set the domain of what is admissible and what is not admissible. So indeed, I mean, you may say that okay, if it's connected, then it's going to give the same answer. That's okay, right? But I mean, I was just giving an example that if the graph was disconnected for some reason, right, and then you ran the DFA on that, and you use one first algorithm versus second algorithm, then it's possible that you get different answers, right? And you define the transfer function in a certain way. Everything is kind of agreeing with what we have discussed so far, yet we can get different answers. But those answers don't going to be like meaningfully different.
Yeah, I guess that was my doubt. So because if the graph is connected with the common entry and common exit node, the boundary conditions will be defined for both the disconnected parts of the graph. So probably I could not explain it. Yeah.
Yeah, so of course, yeah. I mean, if we take the whole discussion in context that okay, this is how we're going to do the DFA. We're going to first define a common entry and then a common exit. Even then we're going to. I mean, look, there could be some dead code, right? For example, if it is if zero something, and we may want to decide that okay, I'm not going to have an edge there or something like that. Or there's some part of the code that never gets accessed, right? You're 100% sure that there's nothing that's jumping there. Now you don't want an entry to go there, right? Because that's not going to be reachable from entry, and that's a disconnected part of the control flow graph, right? And it's possible.
think they still, I mean, at least the first two ones look very similar to me. So can you discuss something more about these analysis so that I can have a clear distinction about them?
Yeah, so
at least the must reach and the reaching definitions.
Sure. So it's all about the application, right? I mean, these are just analyses, and I just define an analysis saying, okay, I'm interested in the definitions that all the potential definitions that could reach this point. That's reaching definitions. Then I have analysis. I'm all interested in all the definitions that must reach this point. That's must reach different definitions. Now, I guess you're asking, why do I need these two different kinds of analyses? And I mean, and then there's available expressions for common sub-expression elimination. So that's very clear, right? I mean, that's totally different. That's expressions. This is definitions. Now you're asking, what's the difference? I mean, what's the difference? I mean, it's very clear that the two analyses are different, right? Must reach and reaching. In one case, I'm asking may reach, and the other case, I'm asking must reach, right? For the same definitions. And I guess the question you want to ask is, what are the applications of these two things? And that would make it clear. In one case, it should be, I would be using reaching definitions. In the other case, I would be using must reach definitions. And for reaching definitions, I already gave you an example, which, the 5-node example, which is basically, you interested in figuring out what are all the definitions that can reach here for this particular variable. And maybe based on that, you want to do some analysis. There are other things that you could do. For example, let's say that there are two definitions that can reach this point for the variable x, and that the x variable is being used heavily in the loop following this program point. Then and one of those definitions actually x equals constant, and the other definition is actually x equals some complex expression. You can say, okay, let me just specialize the two program paths. And because there are only two definitions that are reaching here, let me just specialize the two program paths, one for x equals constant and one for the other one. And for the x equals constant, I can now do constant propagation. That's one more example of an application of reaching definitions. Now let's look at an application of must reach definitions. So for must reach definitions, we are interested in those definitions that must reach a program point. And this is actually very useful for, actually we're going to see later an analysis called dominator analysis. It basically says that, what are all the basic blocks that must reach this point, right? And based on that, I would say that, okay, so for must reach, for example, I will say that, okay, the value that is available at this point, so let's say, is definitely coming from that particular definition. Right, and now maybe I want to decrease the distance of the distance between the definition and the use, or maybe I want to increase the distance. So that kind of analysis can help me. And now reaching definitions wouldn't have helped me in this case, right? So here I'm interested in must reach and not may reach, right? So if my must reach analysis says there's only one definition that must reach here, right? Then we are, that's useful information. I may kind of now do hoisting or sinking and then get some advantage, and reaching definitions wouldn't have helped. Right? So, I mean, these are analyses that kind of plug into some application or some transformation, right? And so these are, and they have their value in different contexts.
Okay, thank you.
Okay, Sonu.
So we discussed about semilattice, meet operator, and partial order relationship. So using these, how do we relate it to transfer functions? That is something, are we going to discuss in the future modules, or is it already covered and I probably did not get it? Just wanted to check on that.
Yeah, so what can you repeat the question? When you say that, how would you relate it to transfer functions? What do you mean by relate?
Or given these things, how can we define transfer function?
Okay, no. See, I've just defined the semilattice so far. The transfer function will be defined later, right? And these are two orthogonal things. I mean, I could have the same semilattice and different transfer functions, right? I mean, they're not using. If I just specify the transfer function, I haven't really specified the transfer. If I just specified the semilattice, I haven't really specified the transfer function. However, that said, there are some properties that the transfer function needs to have with respect to the semilattice, and we're going to discuss that in the future modules.
Okay.
Okay, wonderful. All right. So, more questions, thoughts, or? Okay. So I would just like to say that, everybody who is here is not turned on the video. I don't know why you guys don't turn on the video. I mean, it's just, it's a good idea to kind of have more interaction and stuff. I feel, so please do. Yeah, and I guess, if there are no more questions, let's call it off today, and we'll see each other next week. We watched till module 96 today, this week, and so we have a minor on the. So in the next week we don't have a minor, right, or the midterm, and so we should be able to watch 5 more. So maybe 97 to 101. Yeah.
The minors are next week.
Oh, right. Those minors are next week. So how many days do you have of instruction next week before the minor?
None, sir. Minors begin from Monday.
Oh, from Monday. Okay. So maybe no lecture viewing next week, huh? What would you prefer? Or is that what it is? Or I think let's just cancel lecture viewing next week and resume in the week after that. Right? That makes. Okay. All right. Thank you. And I guess with that, then I guess I should say that the midterm syllabus is going to be till everything that we've discussed today. Okay.
Sir, could you clarify something about the format of the minor? Maybe conduction.
Yeah. So the minor is going to be multiple choice questions delivered over Moodle, and some fill in the blanks maybe, and that kind of stuff. Yeah.
So duration 1 hour.
1 hour. 1 hour duration. 10:30 on 18th. Okay. Thank you. Bye.